In this video, we'll introduce electric field line diagrams. In the last video, we talked about force vector diagrams. For a force vector diagram, we could said there could be a positive source charge, and anywhere in the surrounding space around that force charge, we could represent the force on a test charge with a force vector. We know if this is a sphere of charge or a point charge, a sphere of uniform charge or a point charge, we can apply Coulomb's law, and that is the further we get from the charge, we can use the inverse square law. From the source charge, the inverse square law, the force on a test charge is reduced by that distance squared. The problem with this scenario was if we change the test charge, that changes our force vector diagrams. If the test charge becomes negative, now our force vectors point inward and the length of that vector could be difficult to represent. So instead of force vector diagrams, Michael Faraday came up with the concept of electric field line diagrams. So we'll look at the rules for electric field line diagrams by first looking at this example of a sphere of negative charge. If we look at a sphere of negative charge, we know that if there is a positive charge sitting in the field of influence, or where this source charge can exert an electric force on another charge, if this charge is positive, then it's going to be attracted to the negative charge, and that will be the direction of the force on this positive charge sitting out here in the space surrounding our negative source charge. And our electric field lines point in that direction, in the direction of the force that would be exerted on a positive test charge. So the rules for these electric field line diagrams is that the magnitude of the electric field in this space where the field line diagram is drawn is proportional to the density of the field lines. So notice the density of the field lines is greatest right at the surface of our source charge. As we move away, the density of the field line decreases, and this looks like it would be a circle, but we have to imagine it's three-dimensional. So what we have is a spherical space. In that spherical space, that the density of the field lines is proportional to the surface area of an imaginary sphere at any radial point. So if we put an imaginary sphere right around here, then the density of those field lines will be proportional to the inverse of this radius squared, because the surface area of a sphere is 4 pi r squared. So we'll look at that a little bit further. So that first rule, the magnitude of the electric field is proportional to the density of the field lines. The second rule, the direction of the field is always tangent to the field line. And electric field lines start on a positive charge and end on a negative charge. Since this source charge is negative, we have our electric field lines ending on this negative charge. All these electric field lines are pointing towards in the direction of these arrows. And also the electric field lines are always perpendicular to the surface of the object. That object is the source object. So these four rules we should make sure you write down and are clear with them. If we look at this example, this shows three separate examples of distinct electric field line diagrams. If we look at diagram A, the electric field lines are equidistant from each other. That means we have a uniform electric field. That's also true here in diagram C. They're further apart in diagram C than they are in diagram A, which tells us that the electric field is stronger in diagram A than it is in diagram C. Stronger, that means the magnitude of the electric field of C is less than the magnitude the electric field of A. Or here we have electric field of A is greater than that of C. If we look at distinct points in the diagram, it's also true in diagram A and diagram C, the electric field is the same at point A and at point B. And it's also the same at point C and at point D. And at all points within this region, the electric field is the same. However, in diagram B, the density of the field lines is changing. So as we move to the right, the magnitude of the electric field is decreasing. And if we put a positive charge here, the direction of the force on that charge would be in this direction, tangent to the electric field line. So it's asked us then what is the direction of the electric field at point B in each of the diagrams. What I'd like you to do is write this problem down and bring it to class and answer that question. Now we have another example. We have the same three diagrams, but this figure, it says in each arrangement there's a proton that is released from rest at point A and is accelerated through point B by the electric field. We know that point A and B have equal separations in the three arrangements. That separation, we mean this distance here, is the same in all three of these arrangements. We want to rank the arrangements according to the linear momentum of a proton at point B, greatest first. Well, what is linear momentum? If we recall, linear momentum, I think we usually use rho, that's equal to mass times velocity. What we also have here is that our force on this proton is equal to the electric field times the charge. So that's equal to the Q of a proton. That's the same for them all. That's equal to positive E. So our elementary charge. So the force is going to be dependent upon just the electric field. The proton's the same in each of them. But we will need, for momentum, we need the velocity. So what else do we know? We know that force is equal to mass times acceleration. These are all vectors. This is a magnitude of velocity for linear momentum. Unless we do this, then it's the vector. And we know that the velocity is equal to our integral of A dt. So to compare the linear momentum, since the protons all have the same charge and they all have the same mass, then what we're comparing is the electric field. The electric field in A and C does not change as the proton is moving from A to B. The electric field, so here we'll have a uniform, A and C will have uniform acceleration because we have uniform electric field. In B, we will not have uniform acceleration. Our acceleration, since the electric field decreases, our acceleration will also decrease. So I've started to set up this problem for you. It's a question, so you need to answer it and bring that answer to class. So let's look at some more examples of electric field lines due to different charge configurations. We will review the rules for setting up electric field lines or diagramming electric field lines or reading an electric field line diagram. The magnitude of the electric field density, the magnitude of the electric field is proportional to the density of the field lines. So the magnitude of our electric field is proportional to the density. The direction of the electric field is tangent to the field line. So here it shows our electric field at this point. It's tangent since these lines are straight. That tangent is going to be along the field line. That won't always be the case. Our electric field starts on a positive charge and ends on a negative charge. This being a negative charge, our electric field lines are ending on it. It is the source charge. And our electric field is always perpendicular to the surface of the object. So it's going to be perpendicular everywhere to this sphere, uniform sphere of negative charge. If we look at another example of a charged object, here we have a non-conducting sheet of uniform charge where that charge is deposited on one side. That charge looks like it's a positive charge, so our electric field line starts on that charge and points away, all our electric field lines. So it points away to the right, it also points away to the left. Because it's a positive charge. The direction of the electric field always tangent, but it's also always perpendicular to the surface of this object. So all these, field diagrams are field lines are perpendicular. So if we look at this cross section, if we look at, that's perpendicular. Well, what we learned from Coulomb's law for a point charge we have a radial distribution of electric field lines for a point charge. So if we look at these as continuous field lines or point charges, why do we end up with something that's perpendicular to the surface? So that we will examine later, where more thoroughly, when we look at the superposition of point charges along this surface. So again, this is for a continuous distribution of charge along this surface. We are going to have perpendicular, it's always going to be perpendicular to the surface, so our electric field will be uniform. It'll be uniform pointing away at both sides of the surface of charge. Here we show two equally positive point charges. So these positive point charges have their radial distribution, but we need to, again, superimpose the electric field everywhere in the region. So we do see that it's being pointed away. We see that the density is greatest right at the point charges. It decreases as we move away from the point charges. And if we look at the center of the point charge, there's going to be zero electric field. If these are both the same amount of charge, we have an electric field line pointing in this direction, an electric field line pointing in this direction, but they have the same electric field strength, which that electric field strength, right, is equal to K QS over R squared. If this R is the same distance and the QS is the same distance, they're pointing in opposite directions. So it'll be zero right there in the center. So these two charges are literally trying to push each other away, because like charges repel. So we can see that they're literally trying to push each other away. If we look at any point in this field line diagram, the direction of the electric field is always going to be, we'll do with that in red also, is always going to be tangent. So the tangent to this field line is right here. So if I put a positive charge, the force on that charge is going to be the same direction as the electric field, but this is the direction of the electric field at this point. If we look at this point over here, this tangent, there's the direction of the electric field at this point. There's our electric. So our electric field line diagram, we can get our electric field vector at any given point in this spatial region, the direction tangent to the electric field line, the magnitude, the density of the field lines in that area. This asks what happens to a negative charge at a different space in the field. So if we have, we said if this is a positive charge, well, the positive charge is going to be forced in the same direction as the electric field line. A negative charge is going to be forced in the opposite direction, 180 degrees of the electric field line. Let's look at this field diagram. This is a dipole. We'll analyze this much further. Again, where is the electric field the strongest? The electric field is the strongest. It looks like it might be the strongest at the center here, because we do look at between these two charges. We're going to have the sum of electric field because they're both pointing. Both electric fields are pointing in the same direction. This positive charge is creating an electric field pointing away from the positive charge. The negative charge creating an electric field pointing towards the negative charge. So at the center here, if they have the same magnitude of charge, our E equals K magnitude of Q over R squared. And right here at the center, we're going to have 2E. Because even though it's the magnitude, one's positive, one's negative, but the electric field pointing this way, they're going to sum. However, we're dividing by this R squared. So this is the distance R we're talking about. So the magnitude is actually still the strongest right at the surface of the charges. It's also stronger towards the center. It decreases as we move away from this central axis. We call this the dipole axis. If we have an electron, ask what direction will electron move in this field? Well, it depends where it is in the field. If the electron is sitting right here, this is where we have a negative charge, our electron, it's going to be forced in the opposite direction. So that'll be our F on E minus of the electric field, because the electric field at this point is tangent to this field line. Okay, let's look at one last example. Here it says if the density of field lines at the surface of a uniformly charged sphere of radius r is n, and that's not correct. That should be the number of field lines, so we'll correct that. So we have a sphere of radius r, and the number of the field lines that end at its surface, that's going to be n. It says in the electric field at the surface of that uniformly charged sphere is E naught. Then at a distance of r greater than the radius from the center of the sphere, what is the density of the field lines and what is the electric field? So if we take a radius concentric with our sphere concentric to that, and we let that sphere have a radius smaller r, then we know that our E naught, that's that electric field, that's the electric field at the surface of the sphere, that's proportional to the density of the field lines. So that's proportional to the number of the field lines divided by the surface area of the sphere. So that's equal to n over r 4 pi r squared. What we want to know, what is the density of the field lines at r? So our density of the field lines so if we have density naught then is equal to, so this is our E naught is proportional to that, our density naught is actually equal to n over 4 pi r squared. So the density at r then is going to, we have the same number of electric field lines, right? So the number of electric field lines is the same. What changes is that surface area. Now that's 4 pi little r squared. So the density of the field lines at this sphere of radius r is, it decreases with, again, this inverse square law of the radius. So our electric field then, if E naught is equal to some constant, we'll call it C, rho naught, so our ER is going to be that same constant C, rho r. So we're asked for that electric field at ER. Look at electric field at radius r, electric field at the radius of the sphere, then is going to be equal to, what it's going to be equal to, compare the two densities, that ratio, so it's going to be our 4 pi r squared over 4 pi r squared, or r squared over r squared. So it's relative to the ratios, or we could say that ER is equal to r squared over r squared E naught. So that's a good way to find out what is the electric field at using our electric field line diagrams. We need to know what the electric field line is at one point for a given density. So that's all for this video. We'll work more on using electric fields and electric forces in class.